Hello, friends. Oh, we're really zoomed in, aren't we? Let's zoom out a little bit. Welcome to AI Ethics Part 4, the final ethic, singular. It's super good to be here. It's super good to have you here. And I'm pretty pumped to wrap up our project today. We've got a lot of good stuff today, actually. So wrapping up our project with a sort of final tool to try to debias our algorithm. We are going to take orders from ChatGPT. I will be hopping on one leg and playing the ukulele, apparently. And we will also announce some raffle winners for folks that submitted our feedback forms. So that's incredible. The flower crown is on. Fancy Appleby is not here to tell me to put it on, so I have to put it on of my own free will. But per usual, let me know in the comments what you're drinking. I, again, have some Diet Coke. And it slaps. Okay. You know, now I just live in fear, of accidentally going on at the wrong time, and so I just double checked. We are on time. This is the right time. So welcome. I guess we'll hang out. We'll vamp for a second before we really get into it. But let's see. Did anybody have any questions from last time? I know last time was very hectic, so we'll do a little bit of a review of what we talked about last time today. Otherwise, we are gonna look at some academic papers. We're going to look at some useful libraries, and we're going to get her done. So I guess without too much further ado, we can get into it. Maybe I will grab the notes from part 3 that we had. Where are we? I really need to stop leaving all of my notebooks untitled. It's causing issues. Oh, was it Untitled? No, Untitled 8 was just our first one. Let's look. Oh, it was okay. We're still using the one called Getting Serious. Yeah, okay. This is the problem. When I do name my notebooks, I name them all the exact same thing, which is a choice that I made. Okay. Boom, here we are. Oh, that's really small. I had to change the zoom for the coffee stream yesterday, which shout out to anybody that came and hung out for the coffee stream. That was a blast. Okay, so let's review everything we've done up to this point and kind of set it up to do our final spike down. So we've been working with this loan application data set where we have this historical data from folks who have different credit scores and live in different zip codes and are different races, and we know whether or not they defaulted within some time period, right? And so our boss at the bank we work at has asked us to use this data to predict if new applicants would default on a loan if we gave them one, right? The idea being, hey, if they're going to default on a loan, we shouldn't give them a loan. And we built one. And the model is pretty good, right? But we realized that it has a lot of issues when it comes to we talked about the economics of being a bank. Has a lot of issues when it comes to fairness, right? I believe this is one of our first models that we were trying out, and here, this one of the metrics we looked at was our F1 spread, which is basically just saying how differently do we treat not just the overall prediction of accuracy, but specifically the true positive rate and the true negative rate, right? And the way that we tried to put this into plain English is that if we look at this true positive rate number, that is the percentage chance that you get a loan if you are creditworthy, right? So if you're an Asian person, then if you are creditworthy, you have a 71% chance of getting a loan. For Black person, if you are creditworthy, our model currently gives you a 27% chance of getting a loan. And that is sort of the core of our algorithm being unfair, right? And so we threw that in some math to get this F1 sort of approximate score. And we got that our spread, so the best F1 score compared to the worst F1 score was 0.31. And that is, of course, not great. We don't feel great about that one. So then one of the things we looked at to try to understand why this is happening is specifically looking at, okay, our number if we look at the range your credit score falls in, how good is that as a predictor of your credit worthiness, right? And if you have a credit score of 800, that's actually a really good predictor of your credit worthiness, because it means, hey, like you're guaranteed to pay this loan back. Similarly, if your credit score is very, very low, if it's in the 300, it's a very, very good indicator that you are probably going to default on debt in the future. But if it's in the middle here, that's where our model has a lot of trouble. And we saw that based on our distribution of what kinds of credit scores different folks have, that we end up with a lot of Black and Hispanic folks that are in that range where our model just doesn't work well on them, because the predictor that we have, this credit score value, is not actually a good predictor if it's in the middle. And so we looked at a couple of ideas of how to try to improve this, right? One was generically trying to rebalance the data set and try to remove historical bias by just making sure there are more examples of Black and Hispanic folks in our data set. And that did yield some positive results, right? We got from an F1 score, or an F1 spread of it was like 0.31 down to like 0.27, right? So I want to, that's where we left things. I want to introduce sort of one additional big tool, which is, I think we hinted at it. And there are these two models of fairness called equal opportunity and demographic parity, right? And so I actually want us to create a new notebook. We'll copy some stuff over, but I want to kind of have a clean slate here. So we can just say new. Oh, no, it doesn't like that. Let's go back to our notebook and just click File. File, New Notebook. Boom. And we can call this Part 4. We can call it Global Hack Week 2023, Part 2. O2, Part 4. There we go. And if we okay, so the things we're going to want to copy over into our new notebook, we're definitely going to want to copy our first little blurb, just copying down our data. That's going to be really useful. And then we can import our data like that. We can also copy our bit about splitting or reversing our credit score value, and we can split into our same test train split. And then I want to make sure that we grab our the big function that we wrote where we were evaluating fairness. Excuse me. So we can grab this whole function and bring it over, because that's going to be really useful for evaluating this thing in the future. So now the tools that I want to introduce are based around this academic paper. And if you pulled through on Wednesday, you would have actually gotten, I think, a little bit of a sneak peek of this. There is this academic paper called, let me see if I can pull it up, Equality of Opportunity. Oh, there we go. Equality of Opportunity in Supervised Learning. This is a paper that I believe this researcher actually works in Google Brain. I'm not certain about that. But you can just come and you can download the PDF right there. Boom. Equality of Opportunity in Supervised Learning. This is really the basis for a lot of what this course has been looking at sort of the math put forward here. And I'm not going to make you read this paper. That's, kind of the purpose of this stream, is to make it a little bit easier to digest. But we get to this conversation about achieving equalized odds and equality of opportunity. And you get a lot of interesting math in here about conditional probabilities, and a lot of this math about, like, well, what different kinds of trade-offs can we make? And I will drop that paper in the chat because it is a really, really interesting paper. I would absolutely recommend reading it. But I'm not going to make us do this math, because thankfully there is a really, really handy dandy library that does a lot of this for us. So there is a library called, we've been using scikit-learn a lot, and there is another library called scikit-lego, which is a lot of tools to sort of plug into scikit-learn. But they make it very clear on the website they are not affiliated with Lego, the company, because that would be a lawsuit waiting to happen, I suppose. So what do we want to do? I guess to start, let's grab, I'm going to copy and paste basically our final model from the last time. So I'm just going to drop a huge chunk of code where we sort of generate the vector value here. Boom. So we're getting 72% accuracy. And if we run analyze fairness on our output, or evaluate by race, and if we pass in, if we get predictions, so we can say model.predict, we pass in our test vector, we can get our sort of base model predictions, and then we can pass in our X-trained data frame, our predictions, and then our correct answers, which in this case is X, or this is Y test, are our correct answers. And, issue, Boolean index did not match array along dimension 0. What did I put in that is funky? Let's see. We have Y train. We really should be saying Y. All these things should be our test set here. Okay, cool. So we got our F1 spread of 31, which that's the higher that is, sort of like the more differently we're treating folks of different racial backgrounds. And that's the thing we want to get down. And pull this up here just so we have sort of like this baseline here. So we want to install scikit-lego, which will give us these tools to do that really cool math of equality, demographic parity, and equal opportunity. And so what we can do is we can say pip install scikit-lego, and then we'll import it. I guess we can just pip install first. So we can say from sklego.linear model import equal, oh, hello. Equal opportunity classifier. And the great thing about this is that we don't actually have to deeply understand how this works. But we have already talked about and developed the language of equality of opportunity being the goal of equalizing true positive rates between different groups, and the demographic parity being trying to have the same percentage of folks from each group get the whatever good thing we're doling out, which here is the ability to get a loan, right? So what we can throw in there is we can create a model, and we'll use this equal opportunity classifier, and we'll pass in a few parameters. So the first thing we have to pass in is, because true positive rate is like asymmetric, right? It doesn't like it depends on which thing you said is true versus false. And in our case, we're saying sort of our good thing is being considered creditworthy. And so the sort of positive outcome here is to get a true prediction for is creditworthy. So we have to actually tell our model that. So we can say positive target equals true. So this is saying that like the thing that's nice to have happen to you is getting a true value for our output. We also have to put in a variable called covariance threshold. And I'll explain a little bit more what this is in a second. And we'll start this out with a value of 0.5, but we'll change this in a second. And then the last thing that we have to do is we have to provide a list of sensitive columns. So the sensitive columns list is basically in the matrix that we put in, which of the columns do we consider to be the sensitive ones across which we have to equalize. So in our case, this would be all of the columns that involve race. You might say, well, hey, isn't that just the race column? But remember, we had to do one hot encoding in order to actually get our race value sort of parsable by our model. And so we can grab our X-train. First, let's look at X-train, the data set, or the data frame. So we have credit score, rates, and zip code. And then let's look at xtrain vec and see if we can actually look. Okay, let's say to array. This is probably going to be really, really big. Okay, cool. And let's just grab if we grab the first thing in here. Okay, so this gives us sort of a single line of our data frame from the one hot encoding, right? And so if we do xtrain normal and then just do dot head here, we can see that our first row is the credit score is 616, and then the race is Hispanic, and the zip code is like the second zip code involved. And so if we look at it, we can see, and maybe actually to double check this, we can look at a couple examples. We could also grab the second thing in our vector. So the second person here is white, and so what it looks like we should actually verify this, but it looks like the pattern is we did one hot encoding basically alphabetically by race, and so we have Asian folks is the first digit, and then we have Black folks, then we have Hispanic folks, and then we have white folks, which we could double check this just by printing out the third one as well. Cool, yeah, so the Asian values is the first one. So really our first 4 columns here are all the ones that we consider sensitive. Oh, hey, Adam, welcome. Adam was busy watching crime drama. I'm sorry to hear that. Or actually, it's probably just a TV show that has crime drama in it. I thought you were being like burglarized as we spoke. But I hope that's not what happened. Okay, so we took a look at our encoding, and we now know that our sensitive columns calls are 0, 1, 2, and 3. And we'll plot this out as our EO model. So this is our equality of opportunity model. And we can train it by saying EO model in the same way that we train our old models. We can say EO fit. And what we can pass into our fit is we can say xtrain vec.toArray. And then we can pass in ytrain. This will train our model. Cool. It gives us this classifier out. And then we can say EO model score just to get a high level understanding of how it's doing on x test vec to array and y test. And okay, 0.83. This is really, really good. And this should actually be the first sign that something is not quite right. And in this scenario, the thing that is not quite right is the fact that we are not using a weighted data set anymore, right? Remember earlier we were weighting our data set to say, giving someone a loan who shouldn't get it is actually 5 times worse than not giving a loan to someone that would pay it back, right? And so we need to actually readjust our data set here. Unfortunately, I couldn't find a way to sort of explicitly set class weights on this equality opportunity classifier. So the thing that we can do, it's a little bit hacky, but we can just actually weight our data set. So what we could do is we can use the sample function in pandas. So if we say xtrain.sample, we can pick a fraction of the data set to sample. And if you say something like 5, it'll actually sample like 5 times the amount of data from your original data set. We can say replace is equal to true. So it's allowed to pull the same thing twice, because that's what we're doing is we basically are just saying every row that is a person who did not pay it back, make that appear in the data set 5 times, right? And so then we have to supply our weights. We have to somehow tell pandas that, if you didn't pay a loan back, that actually needs to get weighted times 5. And so we can actually create these weights as a column in our actual data frame. So what we can do is we can say xtrain is creditworthy. So we're going to put our sort of predictor value back in here for reasons that hopefully will become clear in a second. And then we can define a column called weight. and we'll set it equal to xtrain is creditworthy. And then we can say dot apply. So apply lets you run some arbitrary function on a column and return the result of that as another column. And so we can say lambda, this is just a way of writing a quick little function. And we can say, we'll just call it x. And we can use a dictionary here. So we can basically say, if true, return 1, and if false, return 5. And we'll just pull whatever the x value is out of this dictionary. Now, if this lever doesn't make sense, feel free to actually talk through it. But hopefully, just actually seeing what weight looks like makes sense. Or actually, maybe we just do the whole thing. Okay, apparently not enough. Let's say what, 10. Okay, so you see, whenever it's true, we get a weight of 1, and whenever it's false, we get a weight of 5. And so this is our way of just saying, hey, the weight should be 5 times if you didn't pay back a loan, right? So what we can then say is we can say in our weights, we can just set it equal to this column of weight. And we can plop this out as xtrain weighted. If we do xtrain weighted dot head, we should now see in this original one, we saw a lot of trues. So a lot of people who were paying back their loans and not that many folks that weren't paying back their loans. But if we run this, okay, now this is actually great. It's 3 times the number of people who have not paid back loans. And so this actually has changed our data set. So it actually gives us the weighting that we want. Adam said, trains are fun. We don't have trains on the Isle of Man. Well, we have steam trains. Steam trains are trains. It reminds me of, was it Thomas the Tank Engine? Where is Thomas the Tank Engine set? I feel like it's set on a fictional island. I don't know. Drop in the comments if you know where Thomas the Tank Engine is set. Okay. So we have our weighted data set. And note that we're only weighting our input set. We still want to leave our training set just normal, right? We're not gonna mess with our testing set at all. We're going to leave our testing set just normal because we want that to still be like a pure evaluation of how we're doing. We don't want to say, oh, mess with the quantity of different people in that testing set. So the last thing we have to do before we're actually ready to train with this is we have to say xtrain weighted. We have to grab our is creditworthy value out again. So we can say xtrain, or we could say basically y train weighted is creditworthy, and then we can drop is creditworthy from our training set. Because if we trained it with the value literally in it, it would just learn from that value, right? So we can say dot drop is creditworthy, and then axis equals 1. Oh, Adam just sent me an important map. It's the island of Sodor. Oh, this is great. This is great. The island of Sodor is actually in between England and the Isle of Man in this fictional world. Huh. Today I learned. The island of Sodor. Okay. Does anybody have any questions about why we have to take back out is creditworthy? We just needed it in there because we were going to resample, and so we need to keep our labels with our inputs. But then once we actually did the resampling, we want to separate them back out. So now we should still have, after we run this, an x. We can take a look at what xtrain weighted looks like. Cool. Oh, we also need to drop actually the weight column. And key error is creditworthy. Oh, because we already dropped it, of course. Okay, I guess let's recreate it, and then that should work. Awesome. So we just still have credit score, race, and zip code. That is awesome. And then we actually have to do the exact same vectorizing that we did up here. Remember, vectorizing is just taking a bunch of non-numbers and turning them into numbers. And so where was it? Up here, we did our perfect. We did our one hot encoding, and we did a fit and a transform. And if we scroll all the way back down, we can now do xtrain weighted, and we should get xtrain weighted vec, and then we can do xtest weighted. Oh, xtest can be normal. We'll just do xtest and get xtest vec. And now that we're all the way back here, we can recreate our equal opportunity model. And so this number we were getting was unrealistic because it allowed us to not work at a bank anymore, right? And if we don't have to work at a bank, then we could just say, yes, we're just gonna like give houses to everyone, right? And that actually would be great. And I do think that we should think more about how we build houses for more folks. And I think a lot of that is being a little bit making it easier to build housing, like reducing the strictures on zoning and things like that. But all that is not actually, that is regular policy and ethics and politics. But this is AI ethics. And the thing that we can do here is still have that constraint, and within that constraint, attempt to be as equitable as possible. So we're all the way back here. We now have this weighted data set that will basically communicate to the model that that not giving someone a loan is way better than giving someone a loan who's not going to pay it back. And so we can create our model, and then we can take xtrain weighted vec, go to array, and then ytrain weighted? Is that what we call it? Yes, ytrain weighted. And we can build that model. And now we can score it, and we can see how we do, and it will probably be worse, right? Okay, yeah, we're down to 0.71, and this is a little bit more realistic. This is about close to what we were getting before. But so now the sort of accurate, the score that we're getting is pretty similar. But the big pièce de résistance is to check, well, how does this affect our our actual results, right? And we have our, if we come back up, we can grab our evaluate by race. And we can put input data, predictions, and correct answers. So we'll have to generate some predictions. So we'll say x train, oh wait, no. We'll say x test. And then we can say EO model dot predict x test vec. And then we get our EO model predictions. So we put in our predictions, and then Y test is our actual answers. So before we get too deep into this, let's come back up and refresh our memory on what this looked like. In fact, actually, I might just copy this output so we have it down below. Plop it as some text. How about that? Oh, that's not good. Okay, we'll just look at it there. That's fine. So our F1 spread was 0.31. And so our true positive rate was as low as 27% for Black folks, and it was much higher for other folks. And so that spread being 31%. Now, if we look at this, okay, this is pretty good. Our F1 spread dropped down to 0.2. So now, in the previous world, it's if you are actually worthy of receiving a loan, if you are Black, you only have a 25% chance of getting it, whereas other folks have up to a 75% chance of getting it. Now, it's not perfect, but now we see, okay, if you are a Black person and you would pay back this loan, then you have a 38% chance of getting it. And on the other high side, it's like, okay, 65% chance is the folks who have the highest true positive rate separately. So this is, I would say, like, we should feel good about this. This is a success. But there's one knob that we can fiddle with a little bit to try to get this even a little bit better, and that is that covariance score, or the covariance threshold. So covariance is basically just how much two things correlate. And so in this scenario, we're looking at, well, how much does your race correlate with what kinds of outcomes you get, right? And so this is a number that we can tune, and 0.5 here is relatively high. And if we go down to 0.05, this might give us a better outcome. So I want to try 0.05, and we can run this again. Okay, so specifically here, our accuracy dropped like 71 to 65%. But if we evaluate the output, so we were sitting at our spread was 0.2, and our spread goes down to 0.14. And so this is a powerful knob that we can turn, and this is, you know, the whole sort of meta thesis of this track has been that you get to pick what you're optimizing for, and it is absolutely valid to decide to optimize for one thing less and to optimize for something else more, right? I mean, the first thing that we did was we said, hey, we don't want to lose money, and so we're going to turn the knob and we're going to sacrifice a little bit of accuracy for a little bit of profit. And here we're doing a similar trade-off where we're saying, okay, we're going to sacrifice a little bit of accuracy for a little bit of fairness and equity. And so that is what we see is our sort of the how differently we treat different groups. That's how I want you to think of this F1 spread number, that how differently we think of different groups, that is going down. So this was our equal opportunity model. And we got some good results. Note though that we did not get perfect results. There is still a difference, right? If we look at our true positive rate, there is still absolutely a difference between the true positive rate for Black folks and the true positive rate for white folks. And so this, even after using this model, there's still a suggestion that, hey, we probably need to think about other non-machine learning ways to try to improve equity here, right? And to literally improve equity for folks that are not white. So that is a good place to leave that. The one other thing that I want to try, so our accuracy was 65%. We made a little bit of a trade-off for a little bit of accuracy for a little bit of increased fairness. The other thing that I want to try is using their demographic parity classifier. So you can actually look up, let me see, Scikit learn Lego. It's a very cute site. Look at that. Very cute. Actually, I want to look at fairness models. Perfect. And then we have our equal opportunity model that we were just using. See, more math. Let me make that bigger for y'all. More math. Math is great. This is one of those cases where people always ask me, oh, well, I'm thinking about getting into computer science, but I'm not really good at math. And I always say, like, hey, that's great, actually. There's really not that much math in computer science. Where you do get like you can learn to program, you don't need math. Where you do run into math is if you're doing cybersecurity or like cybersecurity research or machine learning research, right? And those things those fields are where you really get thrown, all the math gets thrown at you. So we have our equal opportunity model. And then up here, we also have our demographic parity classifier. So remember that the demographic parity was this idea of not necessarily needling into true positive rates, but just saying, hey, we want equal numbers of folks from different classes to have the good outcome, regardless of who would actually pay back a loan or what they look like on paper, right? So this a lot closer gets to this idea of like, well, should there be some kind of quota for this many folks of this background, getting classified in some way? We talked about why there certainly are some downsides, both in terms of what the performance of your model is going to look like and in your ability to sort of justify this to other people. And that, of course, is like gets back into regular ethics a little bit. But in terms of AI ethics, I think it can be a useful tool to have in your toolbox to show a foil to, well, hey, if we focus on true positive rates and we focus on equality of opportunity, that gives us this kind of result. And then separately, we could focus on just saying what if the probability of getting the good thing is independent of this protected class that you have. Adam does quick maths. So we did our equality of opportunity model, and then we'll do the demographic parity classifier. then I'll hop on one leg, play the ukulele, and announce some raffle winners. Okay, so we can down here. Let's give ourselves a little bit of text and say demographic parity. Boom. So we'll say from sklego.linear model import demographic parity classifier. We'll say DP weighted model. So we'll still use our weighted data. We won't give an easier time on that basis. We'll grab our demographic parity classifier, and then what we'll say here is I suppose we can start. We'll try the same starting covariance threshold equal to 0.5, and then sensitive columns are the same. We'll do 0, 1, 2, and 3. And then, because we already processed our input data, we can do the same thing. We can say DP weighted model dot fit, and we'll do xtrain weighted vec to array. Side note about toArray here. This is a thing that you will run into as you're messing with different kinds of models, especially in scikit-learn. So obviously, we always have to get our models some numbers as their input, and this is this is often called vectorization. But when you are depending on the model and depending on your vector, sometimes you will have a super sparse vector, and a sparse vector is just one where most of the numbers are 0. Right. So a great example of this is if you are oftentimes if you're doing natural language things, your vector will literally just it'll be all zeros except for it'll be a 1 for a particular word. Right. So like maybe if it's the word pineapple, everything is a 0 except for like the 450th slot is a 1. Right. We're kind of one-hot encoding just based on words. But your vector could be, it could be 10,000 spaces long, and all of them could be 0 except for the one that says pineapple. And in that case, we will usually store it as what's called a sparse vector. And a sparse vector is just basically says, you can just leave out all the zeros and just tell me where the ones are in my vector, or tell me where the things that are not 0 are in my vector. And this is really great because it lets us store data efficiently. It's not so great because sometimes our models want to have that whole chunk of memory to manipulate and move around. And so when we say .toArray, that's basically just saying you were storing things in a really nice compact format, but just expand it out and just tell me where all the zeros are, so I have sort of like a fully filled out array. And so that is what the toArray thing is doing. Back to the code. Oh, also, I neglected to share the link. So if you want to follow along and copy code, you're more than welcome to copy and paste what I have written down here. This is not a test. There will not be, there will not be a test at the end. So we have our weighted model, and our DP weighted model. We're fitting it. We want to score it. So we can say DP weighted model dot score. Oh, we also have to include our actual Y-train weighted. And down here we can say xtest vec toArray. And we can say, what's the last one? Xtrain, or no, Y test. Boom. So we should get a score here. Okay, our score is 0.71. This is remarkably similar to the other one. So overall accuracy. Oh, I guess when we weighted, actually, the other one actually had a little bit worse. Yeah, we got down to 0.65. Oh, that's when we adjusted the covariance threshold. Okay, yeah. So we did have 0.71 when we had a covariance threshold of 0.5, which is a pretty low threshold, or pretty high threshold, but it's pretty easy to meet that. So this is basically saying that, like your correlation can be up to 0.5, meaning like, oh yeah, the things can be like decently correlated. They just can't be a strict line. It just can't be, oh, all, like all the black folks don't get loans, all the white folks do get loans. But there can still be a little bit of correlation between those things, which is why we're going to want to drop that later. But we can look at actually making some predictions here. So we can say DP weighted model predict, and we'll pass in X test vec to array. And these will be our DP weighted predictions. And then down here, we can call our, what is it? Not analyze by race. Is it analyze by race? Evaluate by race. I swear. Oh, yeah, here. Oh, yeah, evaluate by race. Boom. And instead of EO model predictions, we'll say DP weighted predictions. And here, okay, so here we get an F1 spread of 0.2, which is, again, actually really similar. When our covariance threshold is high, this actually ends up being really similar to the other one. So now let's try dropping this down to 0.05 and see what happens. Okay, our accuracy drops down to 6.1. So our accuracy actually drops down a little bit further than our equality of opportunity. And we evaluate. Okay, so our F1 spread is 0.1. So this is the lowest F1 spread that we've seen. And this is actually really, really helpful because it allows us to illustrate this trade-off between demographic parity and equal opportunity. So in equal opportunity, overall, we got like a 65% accuracy, which is not too bad. But our spread was 0.14. So to make this concrete, for black folks, you basically have a 1 in 3 chance of getting a loan that you deserve. And then for white folks, you basically have 1 in 2 chance of getting a loan that you deserve, right? But accuracy for everyone is above 60%. Now, if we come down to accuracy or equality of demographics or demographic parity, we can see that, okay, you basically have, a 40% chance of getting a loan you deserve as a black person. And the highest one now actually is Hispanic folks have a 48% chance of getting a loan that they would qualify for. But the accuracy for everyone has gone down, right? So in this case, the accuracy for Asian folks is 50%. It's like a coin flip. Even the accuracy for Black and Hispanic folks is hovering around 70%. And so we have made this trade of, okay, we have actually achieved a little bit more equality, right? We have a little bit smaller spread of that. Well, how are we classifying? What kinds of mistakes are we making on different people? That actually is getting smaller between groups, but we have traded off a lot of accuracy for that. And so this is kind of, getting back to our original idea of, hey, you're working at a bank and your boss is asking you to write this model, but you don't want to be compliant, you don't want to be unfair. This is kind of the thing that you then that you present. We have these different options. There are some important things to do, like we want to rebalance our data set, and we want to make sure that we don't have as much bias in historically what kinds of folks are in our data. But then we have these options to of course we're going to maximize profit, but within that we have these options of how we're going to try to be equitable and be fair. And we have equal opportunity, and we have demographic parity, and we have to make some decisions. And this is, of course, we've been fully in the AI world and just fully in machine learning. But this is where you zoom out and you look at both, regulation and compliance. You look at what other things is your employer as an institution doing. You look at what other policy interventions are there, right? Like, how do we make housing more affordable in general? And you kind of zoom out and look at all these things. But I think the one single biggest thing that we have not talked about yet, which is the idea of trying to get data that actually better reflects the people that you're trying to classify. What I mean by this actually is hopefully a little bit clearer if we come back to this, where was it? Where we do these graphs right here, right? So credit score is just one piece of data that we've collected on our applicants. And we see that it is a better piece of data if you are Asian or white, right? And so hopefully what this process would motivate you and the bank, the theoretical bank that you work for, to do is to say, wow, our models actually just don't work as well on Black and Hispanic folks. And so we should actually try to go out and gather real data that helps us do that more, right? So the like the clear things here are there's a thing called debt to income ratio, which is just looking at how much money are you making, what's your annual income, and currently what are your debt obligations, right? And this is often a number that people actually will put in loan applications. It's usually a pretty important one because it tends to be a better classifier than credit score if you are in sort of the middle of the credit score spectrum. And so this ends up being a powerful intervention to say, hey, from the data that we have right now, we're actually not able to classify everyone from all backgrounds really, really well. And so the thing we want to do is just get more data. This, of course, can, it can butt up against other concerns. You now have to look at that other data and make sure that it is not, carrying some insidious biases with it. And that's the thing that you need to look at. But that ends up being oftentimes a much more constructive place to try to improve your model. Than just saying, hey, these are the trade-offs. Because there are the trade-offs, and we've looked at them, and hey, you can trade a little bit of accuracy for a little bit of fairness, and you can continue to do that all day to the point where I mean, in this model, it's 61% accurate, but it's pretty dang fair. And the way that you try to improve upon that is just by adding more and better data. And so I think that is where we're going to leave it tonight. I obviously would have some other things to do. I think maybe we'll do. Let's see. I guess we'll do the prompt that I was given was. Let me pull it up. It is. I play Mary Had a Little Lamb on the ukulele while standing on one foot and make animal noises for each chord change. So I'm going to, I have my ukulele here. That's easy. Yeah, it's going to be a time. And I'm going to, I guess I should zoom out. Don't judge how messy the room is. Let's zoom all the way out so y'all can see me standing on one foot. And I guess I need to pull up the chords to Mary Had a Little Lamb. I think that's where we're at. Mary Had a Little Lamb chords. I think it's just E and A, actually. So I think this should not be incredibly difficult. Oh my goodness, they want me to turn off my ad blocker. Okay, here we go. It is just A and E. Okay, let me practice for a second. Okay, what are animal noises? Let me get a list of animal noises up real quick. Drop an animal noise in the chat. Actually, that'll be good. Give me an animal noise. Okay, Adam says oink oink. This is your moment. Oh, we got moo. That's pretty good. Got what? Like, what do chickens go? Bok bok, I guess. All right. See if I can actually balance here. All right. Oink oink. Oh wait. Oh. Oink 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 oink. Moo moo moo. Oink oink oink. Purr 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 purr. Woof woof woof. Bok 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 moo. All right, that's it. That's what you're getting. Oh, donkey. That's like what? Like a I saw it just a moment too late. All right, there was our ChatGPT generated challenge, and then I guess the last big thing is to announce raffle winners, and then I'll hang on if there are any questions. But it looks like it's a pretty chill showing today, so I anticipate there might not be many. So if we can get a drum roll out there. So a reminder, these are folks that submitted all 3 of the first feedback forms. I really, really appreciate folks letting me know if I'm going too fast, if things aren't making sense. And I guess the tricky thing is I don't have the I don't have your Twitch username. I just have the first part of your email. So what I'm going to say is I'm not going to say any numbers, and I'm not going to say what domain it's at. So I'm just going to say except for one of them. One of them I know the name, but I'm just going to say like the name part of it. So drum roll, please. The first winner is Adililida. Adililida. Hopefully you know who you are. I have your email, and I'll pass it off to Mary. All right. Drum roll number 2 is email. It's just email and then a lot of numbers afterwards. You know who you are, I hope. And then finally, final drum roll, it's Fancy Appleby. Fancy Appleby won the raffle, which honestly, it's high time because that guy pulls through constantly. If any of you are on the stream, say hey and say congrats. But yeah. Congrats. And if you want to be included, then show up next time for the AI track of Global Hack Week. Yeah, Adam, I think you did sleep before the form. But speaking of which, there's another form which is going to set us up. Obviously, I want feedback on how this session went for everyone, and then also you actually get to vote on what the silly little task is next time. This is actually from last Global Hack Week. I asked people for their ideas, and I got 4 ideas I thought were all pretty good, and they were pick a subject for me to like paint or do art about, pick a song for me to learn on Kalimba, pick a subject for me to write a song about, so like Birds Aren't Real sequel, or pick a message for me to ice onto a cake. So this is not binding, but I think these are all fun ideas. And so I will drop this form. And please also do let me know if things were too fast in this session, if things made sense. And don't you worry, Adam, I will play us out on Kalimba. So I know this is a little bit of a shorter session. Let's zoom back in. I'm way too zoomed out. But oh, hello. Oh, that's really close. Y'all, I cut myself shaving because I'm a little baby. So without further ado, Fancy Appleby is at Disney. That's why it feels so quiet. Yeah, Fancy Appleby just knows how to go out of town right when the stream is ending. Oh, make a new flower crown. Oh yeah, I'll add that to the. Actually, I'll add to the form. I will add like a fill in your put in your own idea. How about that? I'll also just add make a new flower crown. Make a new flower crown, or pick a flower crown style or something. Pick a new flower crown color. Or the last one will just be add your own. Boom. Okay, that is all saved. So please, if you have a moment, fill that out for me. It's always very, very helpful. Otherwise, any questions about algorithmic fairness, about AI ethics, about any of the things that we did in our session today? Honestly, one piece of feedback that I received, I want to say from session 2, that actually is genuinely helpful, is someone said, Will, the name of your track actually was a little bit misleading, which I actually totally get. Originally, the plan was to do like every day we'd look at a new algorithmic fairness thing, and so it's like, oh yeah, we're doing broad AI ethics. And really, I think probably a debiasing a loan application data set, like that really is probably what I should have called it. So for what it is worth, that feedback really got to me, and I'm gonna try to take it to heart and be better about names. Otherwise, if you don't have any other questions, I will play us out, and we will put this track of the AI Global Hack Week track in the books. All right, friends. Happy hacking. Oh, Adam, it's when am I going to learn a new tune? That's actually one of the things that's on the option is to learn a new kalimba song, which you did not vote for that in the feedback form. So I don't know. Get with it. All right. Thank you so much for being here. I love you all. Happy Global Hack Week. Happy hacking, and try to not do evil out there, kids. Bye.